Now we'll look at insertion sort, which is another elementary method that interestingly has quite different performance characteristics than selection sort. Let's look at a demo of insertion sort. For insertion sort, what we're going to do is we'll move an index I from left to right as before, but now in the ith iteration, we're going to move AI into position among the elements to its left. Let's look at how that works on our example with cards. So now we start by initializing I at the first card. And we take the idea that everything from I to its left is going to be sorted, and everything from the right we're not going to look at all. So everything to the left of I is in ascending order. Everything to the right we haven't seen at all yet. So now when we increment I, well, in this case it's already in order. We don't have anything else to do. In the third case now, when I is at the third entry in the array, now we start a index j and we move that starting at I to the left, and what we need to do is just exchange the 5 with every element to its left that's greater. So first we exchange it with the 10. It's still not in place, so we exchange it with the 7. Now we get to the beginning of the array, and once we've done that, or we've hit a smaller element, then we have everybody to the left of I in order. So now we increment I again and we come to the 3. Again, we exchange as long as the card immediately to the left is greater. And once we've done that, then we have everything to the left of I in ascending order. Now in this case we have the 8. We only have to exchange 1, and now it's got the 7 to its left and everything is in order. So we've achieved putting it in order with less work in this case. We don't always have to go all the way back to the beginning. 4, exchange it with everybody to its left that's greater until we find a smaller element, and then it's in ascending order. 2 has to go all the way back to the beginning. But then the very next one, the 9, has to only go back 1 position. And the 6 has to go about halfway back. And then we have the entire array sorted. Again, we can look at insertion sort in terms of invariance. Our pointer still scans from left to right, but now the elements of the left of the pointer, including it, are in order, but the elements to the right have not yet been seen at all. So we have to look at the code that's going to maintain that invariant as the pointer increments. Move the pointer to the right, it's incremented again. Now the invariant's broken because the element on the pointer is not in sorted order. To put it in sorted order, we have to move from right to left, exchanging it with every larger elements to its left. And that's what the code at the bottom does. It starts j at I and decrements j, exchanging j with the elements to its left, a of j with the element to its left, a of j minus 1, as long as a of j is less than a of j minus 1, or j is bigger than 0. And that immediately gives this code for insertion sort, which is similar to our code for selection sort and just as simple. It's got 2 nested for loops. Selection sort had 2 nested for loops, a test, a comparison, and an exchange inside the for loop. And that's a fine implementation of an elementary sorting method. What about the analysis of insertion sort? It's more complicated. Our proposition says that insertion sort, to sort randomly ordered array with distinct keys, it'll use about 1/4 n squared compares and about the same number, 1/4 n squared exchanges on the average. This is more complicated to prove. It depends on the array being randomly ordered. And again, you can get a feeling for where the proposition comes from by looking at this n by n trace. Again, the black elements are the ones that we compare, and actually they're also the exchanges. The red one is the one that's finally put into place. And you can see that for a large array that's randomly ordered, the element that we put into place is going to go about halfway back on the average. So that means about half of the elements below the diagonal are going to be black on the average. There's n squared over 2 below the diagonal. Half of that is n squared over 4. The analysis, exact analysis, is not much more detailed than that. This is a bigger trace that shows, again, about half the elements below the diagonal are involved in the sort. Let's look at an animation. Since n squared over 4 versus n squared over 2, insertion sorts are going to be about twice as fast as selection sort. So we can do about twice as many items in the trace in the same amount of time. It grabs an element, brings it back into position every time. So that's an animation for randomly ordered items. Now, insertion sort does depend on the initial order of the data. Let's look at the best case and the worst case, which are certainly outliers. If the array happens to be already sorted, all insertion sort does is really validate that. Each element has got smaller elements to its left, so it does no exchanges. It gets the sorting job done with just n-1 compares. On the other hand, if the array is in descending order and it's no duplicates, then every element goes all the way back. It makes n squared over 2 compares and n squared over 2 exchanges. So in the first case, it's much, much faster than selection sort, linear instead of quadratic. In the second case, it's slower than selection sort because it uses about the same number of compares, but it uses many more exchanges. So let's see that in the animation. So this is when the items come in reverse order. Now, every time it gets a new item, it has to exchange it all the way back to the beginning. Same kind of dynamic characteristic as selection sort, except for every step, it's not just comparing, it's also exchanging, which makes it even slower in practice. So this is a bad case that we wouldn't like to see in a practical application. But there's also a good case that actually we take advantage of in plenty of practical applications. And that has to do with when the array is partially sorted. To talk about this in a quantitative way, we define what's called an inversion. An inversion is just a pair of keys that are out of order in the array. So this array has 6 inversions. T and R are out of order because R should go before T. T and P are out of order, and so forth. This array has 6 inversions. And we define an array to be partially sorted if its number of inversions is linear, if it's less than some constant times n. And partially sorted arrays appear often in practice. For example, if you have a large array with just a few that's sorted except for just a few unsorted elements appended at the end, it's going to be partially sorted. Or another case is if you only have a few entries out of place, the array is going to be partially sorted. These types of things arise often in practical applications. And what's interesting about insertion sort is that it runs in linear time for partially sorted arrays. And the proof is the number of comparisons and the number of exchanges is equal to the number of inversions. Number of exchanges equal to the number of inversions, and then there's an extra compare for every element except the first. So let's look at how that looks in the animation. Here's a partially sorted array, and you can see that insertion sort quickly gets the job done. We're going to take advantage of this a little bit later in this lecture. That's insertion sort, our second elementary sorting method.